Hi students, in this lecture we are going to continue the wave motion. So in the last class we have discussed up to a medium means speed, right? Regarding speed, a medium in which speed is relatively more, then that medium is called rarer medium, and a medium in which speed is relatively less, then that medium is called denser medium. Now see next one, it is intensity. See how intensity is defined. It is the energy per unit area per unit time. Here condition is direction of energy propagation means wave propagation is normal to the area. Suppose we are taking here, let us take diagram here. Let us take, we are taking a sphere. Source is now at center. Energy propagation direction is normal to the surface we take on the surface of the sphere. If you take any small area on the surface of the sphere, this energy is normal to that area. Okay, so it is mentioned perpendicular to the area. And what it is saying here, intensity defined as energy per unit area per unit time. Now, for point to source, intensity proportional to 1 by r square. Intensity proportional to 1 by r square. See how it is. So if you take now sphere, right? Point source, shape of wavefront is spherical. Shape of wavefront is spherical. Let us say it is now giving energy per unit area, that is a power. P equal to power is P. Okay. So how much energy is crossing per unit area? How much energy is crossing per unit area per unit time? Okay. If you take now this sphere, let us say radius equal to r. We have taken point source at the center of the sphere. Imagine one sphere radius equal to r. This energy spreads uniformly on the entire surface of the sphere. I am repeating, the energy which is coming from the source distributes uniformly on the surface of the sphere. So if you calculate energy per unit area, it is E by 4 pi r square, right? Intensity means it is a per unit time, okay? It is per unit time. And this energy by time, that is a power. So power per unit area, that is intensity, okay? So here there is no energy loss. When you take there is no energy loss, this energy loss, no energy loss means E is a constant, or you can say even E by T, power is a constant, no energy loss. Therefore, intensity, intensity is proportional to 1 by r square. I am repeating, if there is no energy loss, that means there is no loss of power, then intensity proportional to 1 by r square. Okay. And from that we can say amplitude. So amplitude means amplitude of oscillation of the particles. So we are saying that particles vibrate about their mean positions and they have some amplitude, and that is proportional to 1 by r. So why it is 1 by r means, if you remember, in simple harmonic motion we have discussed energy of the particle is half m omega square a square, energy proportional to square of the amplitude, right? In such a case, amplitude is proportional to, so energy proportional to square of amplitude means intensity also proportional to, intensity I'm writing here, intensity is also proportional to square of the amplitude, right? Energy proportional to a square means intensity also proportional to a square. right? That means A square proportional to 1 by R square. Therefore, A proportional to 1 by R. Okay. So for a point to source, intensity proportional to 1 by R square. That implies amplitude proportional to 1 by R. For a line source, see next one. For line source, intensity proportional to 1 by R. You can guess this easily because we are taking a cylinder, right? Energy per unit area. Cylinder area is now, if you take radius is R, if radius is R and length is L, then we can take energy per unit area 2 pi R L surface area, right? And time, that is intensity. So energy constant, or you can say power is a constant. So intensity is a proportional to 1 by R. Intensity proportional to 1 by R means amplitude is proportional to 1 by root R. Okay. Intensity proportional to 1 by R. Therefore, amplitude is proportional to 1 by root R. Right. And if you are taking for a plane wave means area of the wave is not changing. See carefully, when you are taking spherical, as energy propagating radially outwards, radius of that sphere is increasing. So surface area is increasing. If you take cylindrical, as energy propagates outwards, radius of the area of the cylinder is now increasing. Therefore, intensity is decreasing and hence amplitude is also decreasing. But for a plane wave, plane means its area does not change. Therefore, intensity is independent of distance. Hence, amplitude is constant. So, for a plane wave, amplitude is a constant. Okay. So, this point we use while discussing plane progressive waves. Okay. Right. See next one, wave equation. So dou square y by dou t square equal to v square into dou square y by dou x square. This is known as wave equation. This is known as wave equation. If you are saying any function is representing a wave, then that function should satisfy this equation. I am repeating. If you are given any function and if this mention that that is representing a wave, we can say traveling wave, then that function must satisfy this equation. So in this v is known as wave velocity. V is known as wave velocity or it is a phase velocity. Both are same. V is known as wave velocity or phase velocity. And coming to y, it can be any quantity. Remember, y can be any quantity. For example, we are taking now sound. Sound propagates now in a medium. So particles of that medium are oscillating. There we can take y refers to displacement of the particles of that medium. Or we can say when sound propagating, pressure of the medium changes from point to point, then y can represent pressure of the medium from point to point. Or if you are taking a light wave, in light wave is known as electromagnetic wave, where electric field vector and magnetic field vector are oscillating. Then we can take y refers to electric field vector or y refers to magnetic field vector. So y can be any quantity. It depends on the given wave. Okay, right. Next, that is what I have written here. In case of a sound, y can be taken as change in pressure of the medium. In case of light, y can be taken as electric field or magnetic field vector. Okay. And here one important point. Any function, It is a function of position and time that satisfies equation 1, and also finite everywhere and at all times. What is it? Finite everywhere and at all times represents a traveling wave. See, once again, any function that is a function of position and time that satisfies equation 1, and also finite everywhere and at all times represents a traveling wave. Okay, see one question basing on that to understand. It is, which of the following functions represent a traveling wave? So traveling wave means energy propagating continuously. Okay, we can see four functions given here. Now here we have to observe that all four functions are in the form, means they have x and t, right? But if you observe which function is always a finite, means for any value of x at any time. For example, see option B, x minus vt. If I'm taking x value is very large, suppose infinity, square of that is very large, right? So this is not finite. Okay, right. If you take your x minus vt, let us say x minus vt equal to 0, ln 0, not defined, right? Next, 1 by x minus vt. Suppose x minus vt is 0, then this value becomes infinite. But condition is, it must be finite everywhere. Everywhere means for any value of x. And at all times means any value you can take in the place of t. And if you see option A, whichever value we choose for x and t, it is always a finite. Suppose x minus vt value is 0, then e power 0, 1. If x minus vt value infinity, it is 1 by e power infinity, right? It is 0. So whichever value we choose for x and t, that function is a finite value. That's why only A represents a traveling wave. Okay, right. Next, coming to the general solution of equation 1. It is of the form ax plus or minus bt. That is the general solution. And here we are discussing a special type of waves where oscillations are simple harmonic. And those waves are called sinusoidal waves. That means we represent such a wave with a sine function. Okay, either we can say sine function or cos function, both are same only. That means here oscillations are simple harmonic. Okay, those are called sinusoidal waves, right? So now see equation of a plane progressive harmonic wave. Equation of a plane. Okay, important plane. Plane progressive. Progressive means energy is propagating, right? Plane progressive harmonic wave. We are taking now here oscillations are simple harmonic. So we can represent such a wave with the help of a sine or cos function. So equation of a plane progressive harmonic wave is y equal to a sin omega t plus or minus kx plus phi. Here if you observe, we have taken amplitude is a, which is a constant, because earlier we have discussed for a plane wave, amplitude is a constant. Whatever may be the value of x, whatever may be the value of x, amplitude is same. It is a constant. And if you observe carefully here, we have taken here y and this is x. It means oscillations are along y-axis. I'm repeating, oscillations are along y-axis and energy propagating along x-axis. Oscillations are along y-axis, but energy is propagating along x-axis. It may be along positive x-axis or maybe along negative x-axis. Okay, right. Now in this omega, it is angular frequency and its value is 2 pi f, and these things we have discussed in simple harmonic motion, right? And k is known as wave number. It is known as wave number, and its value is k equal to 2 pi by lambda. Okay, right. And here you can see this omega t plus or minus kx plus 5. This entire one is known as a phase of that wave. Okay, right. That is what we have written here. Omega t plus or minus kx plus 5 is known as a phase of the wave. And here one important point is phase of a wave decreases in the direction of propagation of the wave. That means I will write here what it means. Suppose energy propagating along x-axis. This is now x-axis. Okay. And this is y-axis. Let us take at one instant, suppose this point starts oscillating. Let us say at one instant, suppose t equal to 0. This point starts oscillating and energy propagating along positive x-axis. Okay. I am taking energy is propagating along a positive x-axis. Right. Now what happens is if you take one more particle at a distance x that is equal to lambda. Consider at a distance lambda. We have discussed that distance moved by energy during one oscillation is called wavelength, right? When this particle completes one oscillation, energy moves at distance lambda. That means now this point starts oscillating. If you observe, this point has finished one oscillation, and one oscillation corresponds to 2 pi radian, right? And this is just started oscillating. So for this phase equal to 0. That means if you observe along the motion direction, phase is decreasing. If I am taking one more at a distance lambda, then this first one completes two oscillations, second one completes one oscillation, and third one about to oscillate. Then its phase becomes 0, its phase becomes 2 pi, and its phase becomes 4 pi. Okay, that's why phase of a wave decreases in the direction of propagation of the wave and vice versa. Its meaning is if you take opposite to the direction of propagation of wave, then phase increases. Okay, right. Now see here, the equation of a traveling wave in positive x direction is given by what we are saying. It is in the positive x direction. Then we are writing as it is omega t minus kx plus 5. Omega t minus kx. Why we have taken minus here? Because along the wave, phase has to decrease. See carefully here at a given time. When x value increasing, phase is decreasing. Getting the point? If you take at a given time, as x coordinate increasing, omega t minus kx decreases. So phase of the wave is decreasing. X coordinate increasing means energy propagating along positive direction of x-axis. Okay, right. Now same equation can be taken as, we can see you can take 2 pi outside, it becomes t by t minus x by lambda. Okay, suppose we are taking k outside, If you take k outside, this becomes v. This v stands for velocity of the wave. Okay, na? And what you call that velocity of the wave is given by omega by k, and this we discuss now. Okay, so it is becoming k into vt minus x. Okay, or if you take omega outside, it becomes t minus x by v. I will discuss this one. Okay, in the next slide. Right. Okay, now we are discussing here one special case, that is now transverse waves along a stretched string. What is that? Transverse waves along a stretched string. That means take one long string. Let us say one end is a fixed. It is long string. And let us say we are oscillating at the other end by keeping the string tight up and down. Then energy propagates along the string, and we're having that wave is like this. String shape becomes like this. Okay, means oscillations are along y-axis. Let us take string is along x-axis and oscillations are along y-axis. Okay, so here we are taking one important assumption, that is tension is the same even after the deformation of the string. So initially we are holding the string tightly, so there is a tension. But if you observe, when string shape is now like this length is now greater than the length of the string, right? That means string is having elongation. So when there is elongation in the string, its tension changes. When there is an elongation in the string, then its tension changes. But we are saying tension is the same. So this is possible only for small amplitudes. This is what we call amplitude. For small amplitudes means string length almost the same. Okay, that's why I have written here note. The above assumption valid only for small amplitudes. The above assumption is valid only for small amplitudes. Okay, right. Consider the string is stretched along x-axis and it vibrates along y-axis. That is what I have discussed, right? So I assume energy is propagating in the positive x direction. Then its equation is a sine omega t minus kx plus 5. This is the equation. Right. So here we take one assumption. If we assume that there is no energy loss, there is no energy loss during the propagation of energy, then shape of the string should be same. I am repeating, if there is no energy loss during the propagation of the energy, then shape of the string does not change. It is always the same. See carefully, I will explain here. Suppose, suppose string is like this. Shape of the string is like this. Whenever we are taking this shape remains the same. If you are taking, there is no energy loss. If you consider any point on the shape, its y coordinate does not change. If a shape is not changing, if a shape is not changing, if you take any point on the shape, its y coordinate does not change. Okay, that means that means what we can say here. Derivative of the phase should be zero. The phase is constant because y equal to a into sine into the phase. Y value constant means that phase value is constant because when it propagates along positive x-axis, x coordinate increasing at the same time is now increasing. So omega t minus kx is a constant. So we have taken derivative of that phase and that should be equal to 0. Okay. And from this what we get? From this we are getting d by dt of omega t, that becomes omega minus k into dx by dt equal to 0. From that we get dx by dt is equal to omega by k. Okay, omega is a positive constant and k also positive constant. If you observe dx by dt positive, its meaning is x coordinate is increasing. X coordinate increasing means energy propagating along positive x direction. Okay. If you get negative, that indicates energy propagating along negative x direction. So this V is known as wave velocity or phase velocity because we got this by differentiating the phase. Okay. Right.